So welcome to this webinar on cloud computing and geoscience, its mysteries, miseries, and benefits. So why talk about cloud computing and geoscience? This is because in geoscience we have an enormous amount of highly diverse data. A very small portion of this is being used in daily work, but it is there to exploit, to obtain new insights, and to support decisions related to the geosciences. This is just an example of the released well database from Norway, exploration wells only. And even with such a filter on your data, this is thousands of wells. You can look into all the data types that exist for all these wells. So we have the measured logs, for example, and the porosity logs, which are derivatives from the measured logs. We have the core samples, core photos, and all the data measured in labs from the samples of rocks and fluid taken in all these wells. So it's getting quite huge, even looking at well data alone. And it makes sense to use cloud infrastructure to make this available to those who need it, to the domain experts and to the decision makers. Exploiting cloud infrastructure in geoscience is in kind of early adoption stage. The ability to do so has been around for a few years. Now, several early adopters are working hard to deploy cloud solutions in their companies. But we believe that this will change and that this will become mainstream, and we will see a transition in the coming years to high-scale adoption. So what is cloud computing? You could say that cloud computing is about delivery of on-demand applications, delivering computer resources without having to manage the infrastructure yourself. And why is it useful? Now in the age of AI and machine learning, it is a very good infrastructure platform to deploy machine learning systems. We have cloud-native applications that are built specifically to run in these environments and to be accessible to the users in the browser. We know this technology well from private consumption of services such as Netflix, Amazon Prime, and even from software such as typical office software that we use, for example, the offerings from Google. And there are still some mysteries around this concept of cloud. So it can come in many forms, and one of the forms is basically a remote desktop service. So this simply means that one deploys software that was originally built to run on desktop computers in the cloud on remote machines. So you can deploy any traditional application to run on a remote machine in a cloud environment. But there are some drawbacks to this solution. You have to pay for having this remote machine up and running all the time. So it's computationally and memory resources are underutilized when you don't actually use it all the time. So it leads to high rental costs. And when you deploy multiple applications in this manner, there is no system that allows interaction between these applications and their storage systems. So you don't solve the data silo problem. The data is still locked in the storage systems of these legacy applications. And in contrast, we have cloud-native solutions, meaning software that is specifically built to work in cloud environment. This is deployed directly on the cloud infrastructure. Storage and compute is on demand. You pay for what you use. You don't have to pay to keep things running all the time. So in many ways, this overcomes the shortcomings of these remote desktop scenarios. It also allows you to liberate the data and allows data contextualization and sharing and distribution on another level. It allows you to elastically scale your access to compute resources. We see that the demand is highly variable from day to day and week to week. So this is a real cost saver, being able to pay only when you use these resources. There are also many types of cloud, even if we're looking into the cloud native space. It comes in the form of private and public cloud services. There are hybrid solutions, mixtures between private and public, and there are also multi-cloud solutions. So the private ones basically means that you can deploy a cloud setup on hardware that you control yourself within your organization. You have full control of everything. But of course, in that case, you have to have an organization that manages it. So that is what you don't have to if you go to the public cloud. The public cloud vendors will take care of a lot of have systems that facilitates things for you. Some of the operators in oil and gas have been a bit reluctant to go to public cloud, partly because of worries about cost and partly because worries about data security. And then we can bring in the concept of hybrid. So it is possible to keep the large data sets, for example, seismic data, stored on premise, and use the public cloud infrastructure to access compute. So then you have your seismic data where you originally kept it, but you gain the access to the elasticity and the availability of compute resources, such as CPU and GPU. And it's also possible to mix the offerings from multiple cloud vendors. So when you want to access compute resources, you can get these from whoever you want on the spot when you need it. So from Google, Amazon, Azure, and many other providers. So there's a lot of flexibility in the way you can deploy cloud systems. So one barrier we have seen in geoscience has been data formats, and this is kind of getting solved, or it's being solved right now. And we have seen in the past a high dependency of a format such as SegY for seismic. This was originally designed for data exchange and storage rather than processing. So in data processing and even data visualization, we need formats that allow rapid, random access to whatever slice or sample from a seismic volume that you want, and that you do achieve with these new formats. These new formats, of course, also allow compression, so that they reduce the data size. And some of these formats are examples are mentioned here: HDF5, NetCDF2, and these are kind of bricked seismic formats that allow large compression rates. There is also a need to kind of standardize a bit on when it comes to well data, seismic horizons, metadata, and other data types. And a lot of this is being handled, so this is not really so much of a bottleneck anymore if you decide to go cloud native. So one of the reasons why to use cloud systems, I mentioned there was to facilitate AI and machine learning. And one of the pillars of machine learning and the growth that we have seen in domains outside oil and gas is availability of compute resources, CPUs, GPUs, high performance computing on demand.
Auto shutdown initiated.
The two other pillars are, of
Auto
course,
shutdown
the
canceled.
big data.
Mic on, mic off.
That allows you to train robust generalizing models. And of course, the machine learning algorithms themselves, which are being openly accessible through publications and GitHub and other sources. And it's easy to get hold of code that you can adopt to specific use cases. And in geoscience space, in Earth Science Analytics, we have adopted these principles like this. So we access compute from multiple vendors on demand. Data is available on a large scale from national data repositories such as Discos. We have data exchange systems, data management APIs, such as those coming from OSDU. We're building custom layers on top of all of this to really provide the data at the fingertips of those who need it in the form of our EarthBank data platform. And of course, when it comes to the algorithms, of course, we strongly leverage the open source progress in terms of the software libraries in Python and from TensorFlow, scikit-learn, all of these, and we adapt these to specific use cases in geoscience and provide these through our EarthNet data analytics platform. So just an example here of computational resources on demand. We need this just both to train machine learning models and also to execute them on some data. This is fully elastic. You just go into the system and click which type of resource you want, which region you want it in. You fire it up and it's ready to go very quickly. So then this benefit together with the contextualized data really enables using machine learning technology on all the data types within the geosciences. The data that we have available is increasing at a very high pace. So we, of course, know there's a lot of data in the form of well logs and seismic data. But an example here in this image is photographs of cuttings samples. So that are being made available for all the exploration wells in Norway. So this is a new data source that needs to be distributed to those who need it. It needs to be interpreted. And the example on top is an example of how machine learning has been used to automatically interpret the fragments of rock in such an image. This initiative is driven by the Norwegian Oil and Gas Association, and this type of data will be made available eventually through the National Data Repository of Norway, Discos. In cloud native solutions, we definitely want to eliminate the silos. We need rapid access to any slice of the data, just illustrated here with a random line through the seismic volume with some logs plotted on top of it. So this really needs to be available on a single click or a few clicks within a minute. So to get around the problems we've seen in the past where geoscience practitioners have used so much time to locate data before they can even begin analysis. With these new systems, the data is there at your fingertips, the compute is there at your fingertips, and you pay only for the resources that you need when you need them. So this opens up for a very diverse portfolio of data analysis methods, visualization. You can plot whatever data you need in seconds, whether it is like GIS type geographic information type plots in maps, if it is well bore plots like illustrated here. The AI systems, as we know, can also automate the seismic interpretation of faults, geobodies, and horizons. And we can even bring the ground truth information all the way from the core, the samples of rocks and fluids analyzed in the lab, to the seismic scale, and even to sub-basin scale, linking data types from samples via logs and then all the way to the seismic scale. So thank you for joining this webinar. For further information, you can contact Earth Science Analytics at the email listed here, or visit our website, earthanalytics.ai. Thank you.